So what I'm going to cover, I guess, in the next hour and a half is how we've at AT&T used all the things that Patrick talked about. He probably told you about Llama. It's the toolkit that he has built on all the theory that he has talked about for NLP tasks. And some of you know those tasks, some of you don't. But in the first part, I will try to bring us all onto the same page, go through all the NLP tasks so that we understand what we are dealing with, and then instantiate some of those tasks and model them using the Llama toolkit. Okay. So I guess first I have to figure out to work that. Okay. So general background on NLP and NLP tasks, and then a bunch of tasks that we've done, including sentence segmentation, classification, and so on and so forth. I picked these tasks with some intention in mind, and maybe that will come out in the talk or maybe not. It has to do with the kinds of features that get used in the modeling, and also the data structure that you work with. And we'll go through, and it might become clearer as the talk proceeds. Okay, so just to set context, so in spoken language processing, when the input is speech, it could come from telephone conversations like we have in AT&T. We have a lot of call center data where people call in and say, oh, I have a problem with my bill. I don't understand why you charged me XYZ. Okay, a typical call. Or it could be a news broadcast saying, Hillary Clinton pulled out of the presidential race, blah, blah, and so on. It could be voicemail messages saying that, oh, Srini, I'm trying to reach you, where are you, and so on and so forth. Movies, we all love them. So there's a lot of movie data. So what we try to do is to process that. By processing, I mean try to convert it into some structured form where we can do searching, browsing, retrieval, understanding, whatever that means. Okay. So in the big sense of the word understanding. So the first step that happens is a speech recognition. We get a speech recognition output, and this is usually a single stream of text, or it could be more complicated representation where you have multiple sentences that were recognized with or without weights and so on. So those complexities are hidden there. And then we have a bunch of NLP tools which take that output and produce some sort of a richly annotated text. And I'll go through the set of tools in the next few slides. And then once you have a richly annotated text, then you can do a task-specific mapping, transduction, into one of these many applications like summarization. How do you, take a news broadcast of, say, an hour and summarize it into a 10-minute snippet? Or machine translation, take a Spanish movie and show it in English, okay, things like that. Question answering, information extraction, things like that. The same thing you can think of in the text world, where the inputs are textual documents or web documents or email messages or blogs. The difference between speech and text is that when you look at the pipeline, the first box is slightly different. Okay, the first box in speech input is a speech recognition system that produces a an output here, which is typically very noisy. Okay, in the text world, it is a little less noisy, but still there is noise, partly because of segmentation and various formats of your web document, or should we be tokenizing it here or there, and these are issues that create ambiguous representations of the text. And the rest of the pipe pretty much is the same. You can, once you have some ambiguous representation of the text, like in the speech world, then the rest of the pipeline stays the same. And again, you can apply the same kinds of transductions to produce various applications, summarization, machine translation, and so on. Okay. So basically, this is the big picture. This is why we are in this business. We take input of text or speech, transduce that into some meaningful structured representation, and then write some transducers, some mapping functions to take that structured representations into things that are meaningful from an application point of view. Okay, so think of this as the application layer. Okay. All right. So what is that pipeline like? Quite a few of you who have done an NLP course might recognize this sort of set of boxes or beads on the string. People who have not seen it, you'll see it. I'll go through them stepwise. So first thing is tokenization. So given text or speech, you have to chop it up into some units. And it is controversial. What is that unit supposed to be? In text, maybe it is a sentence. Okay? And maybe a period is a good marker for a sentence boundary. Sometimes periods are ambiguous. So, like an abbreviation, should we be segmenting it there or not? So it's a decision you need to make. Sentence segmentation is typically that. Let's see there. US President lives in Washington, D.C. He will travel to Florida this week. So you want to segment it into two sentences. D.C. has supposedly, you should have written it into two periods, but nobody writes it with two periods, right? So that has sort of become a one single period. You don't want to break at US President just because you saw a period there, right? So it's a decision problem. Again, we have to train or write rules, and typically people do write rules. Okay, people, when you go to a language where there is not much data, you may have to write rules, and there's nothing wrong with it, right? Here's part of speech tagging, which you might have seen, where you have to annotate words with the part of speech, and part of speech are simple parts of speech are like nouns, verbs, adjectives, prepositions, adverbs, conjunctions, and so on. It so happens that we have a resource called the Penn Tree Bank, back from the days when Jason and I were at Penn. We had created a resource that had annotated about 1 million words with parts of speech information, okay, and more syntactic information. But we have about 40 tags instead of the 13 that I mentioned, the simple parts of speech. We have a little bit more refined part of speech tags. The idea behind part of speech tags is to disambiguate, again, towards building a structure, right? If I say the word bank, should it be a noun bank or the verb bank, like the bank of a river versus to bank on you to do this assignment, let's say, right? So disambiguating, again, keep the big picture in mind. You want to transduce this unstructured stream into some structured form. And the structured form involves extracting as much information as possible. Extracting whether it's a noun or a verb is one kind of information that you're trying to extract, right? Named entities. These are so-called interesting items in the text, right? So I might be interested in knowing the names of people and places in my text, or dates, okay? So if I have marked it up here. President Bush will travel to Florida on February 20, 2007 to meet the CEO of AT&T. Made up sentence, okay? And I've annotated each the entities that I am interested in. There's no fixed vocabulary. I mean, if you may be interested in things like company names, or you may be interested in services that AT&T provides, and those could become named entities, right? So there's no God-given set of named entities, but typically the community is interested in names of people, dates, place names, maybe positions, job titles, maybe company names, okay? These are some of the things that generally people are interested in, okay? But if you were running a back-end service, customer service operation, you may be interested in very different kinds of things, okay? But the general idea is you want to annotate some part of the text that you're interested in with one of these colors, one of these tags, okay? There is kind of the similar thing towards getting the syntax extracted out. You want to do some sort of pre-processing of the text to detect groups of words that form noun groups or verb groups. Okay, in English, the modals are not written in as single words but with spaces. So maybe you want to put them together. In language like Hindi that I know, verbs and their inflections are written together. Tense and aspect markers are all written together as single word. So you may want to pre-process the sentence to create such chunks, verb chunks or noun chunks. So essentially you're simplifying the sentence by grouping these. Think of it as another form of tokenization, right? So you're simplifying the sentence so that the next step has an easier job, right? Here's syntactic parse. So given that I have simplified the sentence into dollar person, so variable name, blah blah, and dollar place, dollar date, how do I recover relations among words? Okay, now I'm going one step further. I'm saying that not only are you segmenting these sentence words into groups, but I'm also trying to give you relations between words, okay, or among words. Here's what we traditionally call a hierarchical decomposition of the sentence into, it's also called a dependency tree, okay. So you're trying to break the sentence down into these relations, okay, and sometimes these edges are labeled by the relations. It's a subject or an object or an adjunct, meaning modifier, and so on. So those are called labeled dependencies. So next step down the lane, there you go. So this is called semantic role labeling. So these are typically, people do argue about the label and the meaning of a label, and sometimes it's very application dependent, okay. So sometimes you might want to label this with some application specific label, but essentially you're labeling that relation and saying that these two words are in this relation, and you want to recover that so that the next step, when you're interpreting it, you have an easier time, okay. So again, this is another decision making step. What should that decision be? What should that label be? Okay. Word sense disambiguation. So we talked about bank versus bank as a verb or an verb or a noun. You can have bank versus bank, the two senses of the word bank, of the noun bank, a financial bank versus a river bank, okay. And given the context of the sentence, you will be able to tell usually what the sense of the word is, whether it's a river bank or a financial institution, okay. Partly because the surrounding words set up the context, and usually it disambiguates one way or the other, okay. Again, this is a decision problem, right? So the theme that I'm trying to get, okay, so the last step. Here's co-reference. Co-reference is, it's like variable equality in programming. If you were to equalize two variables, that's what we are trying to do here, that the US president lives in Washington, D.C. He will return to the capital this week, and I want to know that the capital and Washington, D.C. are the same, okay? And why do you want to do this? Any thoughts? Inference for...
So you can draw connections between, or maybe do summarization over sentence, or
right,
what things are talking about.
Sure. So imagine that you were searching for Washington, D.C., okay? If you do a grep, sure, you can get this one, but you'll never get this one unless you establish that these two are the same, right? So that's an useful utility to have, in things like web search, right? So these are things that NLP worries about, and the underlying theme is that all of these steps that we talked about are decision problems. Okay, there is some decision that is being made either at the word level, as in part of speech tagging, or at the substring level, as in chunking, substring meaning sequence of words, or at the tree level, as we saw in the syntactic structure. Okay, so these are typically modeled by things that Patrick talked about. Okay, and we'll go through a few examples on how these decision problems are done. Any questions so far? Absolutely clear. Okay. Okay. So what we have at AT&T are two sort of a toolkit for natural language processing, which encodes some of these things that we talked about. So at the foundation layer, we have the classification tool that Patrick talked about, which is called Llama, and there is a finite state modeling toolkit. I don't know if you're going to go through a finite state class, but it's a way of encoding strings and sequences in a in a state chart representation, okay, with states and arcs, and these arcs could have weights on them. Okay, you might have seen that in your automata theory class, maybe. Okay, some of you. So there is an algebra on how to combine finite state machines, how to intersect these machines, how to invert these machines, and you can think of them as acceptors, meaning they take a string and say, yes, this is in my language, or no, this is not in my language. They could assign a weight to it, saying that, okay, with some probability p or cost p, this is in my language. We could also have transducers which map one string to another string. So take an English string and map into a Spanish string. Okay, so which means that the arcs on the finite state network have two components, the input side and the output side, and each arc can be weighted. Okay, so that's sort of the foundations for everything that we have. Then there is a layer, what we call the algorithm layer, which for better or worse has things like text classifier. So given a bunch of stories from, say, Reuters, sports stories, finance stories, international politics stories, and so on and so forth, can you classify them into these categories? Okay, as a whole chunk, as a discourse, a piece of text, can you assign a label to it? Okay, most of what we talked about in the preceding few slides was at the sentence level or the word level. So I didn't say much about the text level. Some of the things that we do in the text classifier is at the text level. So given the whole text, meaning a multi-sentence text, can you assign a label to it? We also have a parser, which gives you the syntactic representation, the dependency representation. We have a chunker, which is also called as a shallow parser, a sequence tagger for things like part-of-speech tagging. Okay, so that's the algorithm layer. And then we have various models built on these for the various tasks that we talked about. So for sequence tagging, we have part-of-speech tagger, chunker, named entity tagger, and I'll talk a little bit of super tagger. These are all kind of sequence-based tagging problems. Okay, given a sequence, produce another sequence of labels. Okay, and then there are semantic role labeling problems, and there is the co-referenced word sense disambiguation and things like that, which are more global in a sense, beyond just single sentence, multi-sentence problems. And then the application layer, we have prototyped a few of these: summarization, translation. Given a speech call that comes in, can you tell that it's a billing related call versus a troubleshooting related call versus a new customer call, that kind of call type classification, and how to automate emails from customers and things like that. So that's sort of the how architecturally these toolkits are organized, just to give you some flavor of what this is like. So Patrick might have touched on classification in his talk. So one specific example we have, I just told you about, is taking a speech output related to what a customer is calling about, and then sending it through Llama to find out, which bucket to put it into. Okay, whether it's should I be routing it to the billing department? Should I be routing it to a new service department, and so on. And typically, what we do is we do some sort of normalization. We're removing partly speech is very different from text in the sense that spoken utterances are not usually grammatical. Okay, there are lots of disfluencies, meaning ums and ahs and restarts, like what I just said, filled pauses, okay, dead silences, things like that. And people reword their request in many different ways. And that's a bit of a challenge, and I'm sure you have one or two examples of that. Entity extraction we saw, if I were calling about my bill and I say, I got the wrong bill in the month of May, I want to know the bill date was May, and I want to pass on that information to the next step or to the human agent who's looking at it. So extracting named entities from spoken language data is critical here. Are there questions there? Am I going too fast? You're okay? Okay. All right, so the other kind of problem is sequence tagging. So that was more like a global text, and I don't want to delve into that part, because most often what we do is you take a treat the text as a bag of words, or a bag of word triplets, or word, tuples, consecutive word tuples, and then train a classifier to say, whether it's a, call type 1 or call type 2 or call type 3. There's not much analysis that is done there. But a lot of NLP problems can be formulated in the sequence tagging framework, where you have a sequence of tokens and you are mapping those sequence of tokens to other sequences of tokens. So part of speech, for example, so the general problem looks like this. You have a word and you have a tag, a word, a tag, a word, a tag, and so on. So once you have a new problem and you kind of encode that problem in this framework, then you have a whole range of tools that you can apply on this encoded problem, okay? And we'll see a few examples of it. So for example, part of speech tagging is very clear. The TIs here are basically, noun, verb, adjective, or, NN, whatever the tags that you make up. So that's pretty clear that it is like, President George Bush will travel, you have NNPs, and each word has a clear tag. Named entity is less clear unless you sort of see this encoding. What you do is, or syntactic chunking, both problems have this bracketing nature. So what you are trying to do is to take the sentence and chop it up into segments. Okay, that's the chunking problem. So you're drawing a left bracket here and a right bracket somewhere else in the down the stream. What you do is to try to encode that bracketing problem as a tagging problem, so that each word gets a tag, either saying that it is inside the chunk, meaning inside that noun chunk, or outside the chunk. Okay, so those two are pretty clear. Or it could be at the boundary of two chunks. Okay, so with these three tags, you can sort of encode the bracketing segmentation that you are looking to get. Okay, so in this case, I'm interested in detecting George Bush as a person. So I might encode, assign the tag O, meaning it's outside and I don't care, to the person tag for president. George gets the tag for person, and Bush gets the tag for person. So and then you can now reduce this problem, and it starts looking like the part of speech tagging problem, where each word has a tag. Okay. We'll come to these problems a little later. Was that clear? Okay. So in general, this kind of tagging problems can be modeled as follows. So given an input sequence like this, you want to produce an output sequence of tags which is of the same length, because each word gets the same, each word gets a tag. Okay, so this is kind of crucial that these two ends are the same, and the order of these tags matches the order of the words. So each one gets one tag. Okay, then we'll see another problem like in machine translation where you can also model this as a tagging problem, except the n and n here are two different ones. So you'll have a different sequence of words in English and a different sequence of words in Spanish. Okay, so the two n's may not, the lengths of this two sequences will not be the same. Okay, so all members are from some predefined set of tags, which is called the vocabulary, tag vocabulary. So it could be 13 tags for part of speech, or the 3 tags that we talked about for named entities, okay, and so on. And what you're looking for is some sequence of tags that, given the word sequence, maximizes some score, okay. You see, so this is basically a search problem. You're searching for that tag sequence that maximizes this, happens to be a conditional probability. Okay, and to estimate that, what is typically done is what is called a Markov assumption. That means I'm not going to take the whole sequence I've seen so far into account, but I'm going to forget some of the history. Okay, so I'm going to take only maybe 2, maybe 1 of my preceding decision that I've made. Okay, so that's what this Markov assumption is, that I'm going to make some independence assumption saying that this whole sequence can be chopped up into some small bounded sequence of decisions, and that's what this assumption. Now, however, we can generalize this and say that I'm going to take any feature function, which is phi, okay, of this context. So this is the context that I'm trying to use to predict the TI, and I can take any feature, and by any feature I mean things like, it probably is on the next slide. Okay, I just go through this. So this is the history with 1. You could have history with arbitrary, depending on how much data you have and so on. You could have arbitrary amount of history that you're conditioning on. And what you're trying to do is to learn this scoring function, which says that given this history, what is the score for this tag look like? Okay, and that will tell me how to go about tagging that word. So and the feature functions, these phi values could be an arbitrary things that you compute on the context. Things like I can take n preceding words, n succeeding words. Okay, so I could take 6 words to the left of it and 6 words to the right of the target word, and see what the words are. If I saw a Mr. in my left context, then it's most likely going to be a name of a person. If I saw a to or a from in the left context, and maybe the word city on my right context, maybe it's the name of a place. Okay, so these are sort of the feature functions that you make up, or you let the program build out. You could either encode them as rules and then ask the program to refine those rules, because you obviously that Mr. example may be 90% right, maybe 10% there is error. But maybe you want the system, based on the annotated data, to learn what the confidence it should assign to that rule. Okay, so those are things that you kind of try and encode, and so it looks something like this. You have some feature function on each of the context words, and then you may want to take one decision history. Okay, T being the preceding decision history. The other examples of contextual, the 5 feature functions could be, is this word capitalized? Okay, and typically proper names are capitalized, so that's a good feature to have. Does it have a period in it? Okay. Does it have a hyphen in it? Is it a number, digit sequence? So these are some of the feature functions that you may want to consider. So here's a bunch of things. So for the word limited, LTD period, these would be the settings of these feature functions. It's an uppercase, it's all caps is false, lowercase, and so on and so forth. So these may be some of the lexical orthographic feature functions that you may want to consider. Okay. And the utility of this is basically if you had seen a word, then maybe the word itself is sufficient. You don't have to generalize to these feature functions. But if it is an unseen word, a new word, but has the profile corresponding to these sort of feature functions, then the system will probably generalize better. That's the intuition. Okay. Any questions? All right. So if you were to just take the feature functions into, or what I call static functions, meaning you're not conditioning on any decisions that you made in the past. You're conditioning only on the current word and its surrounding word context, because the word context is already given to you. You're not making any decisions about it. Then you don't have to build a search network, meaning to find the best sequence of decisions. Okay? But if you were to condition on some preceding, like we saw, one history, then you build a search network of this sort. You know, I may say, okay, the first word should be either T1, T2, and so on and so forth, Tn, and if it were T1, the preceding decision, the next decision is conditioned on T1, okay, and so on. So this condition is again conditioned on T1. So this becomes the history of decisions that you are considering, okay, and this results in a search network, so which you have to search through to get the best sequence of decisions from the beginning to the end. Okay, and the scores that are computed here could be either generatively trained. Jason covered HMMs yesterday, which are generative models, or it could be discriminatively trained, like what Patrick covered the preceding lecture. Okay, but if you don't have a conditioning on the preceding decision, then you don't need to build the search network. Okay. Okay. So let me switch gears. Any questions so far? Was the sequence tagging fairly clear? I see some blank faces. Okay. All right. So let's move on to look at some of the applications or the tasks. One task is called clause structure. So we want to break down a given piece of text into clauses, and clauses, roughly speaking, are the verb and its arguments, meaning subject, object. So we want to break down this kind of piece of text into something that looks like this. Okay, that certainly the chancellor that has made it clear that, and a clause if, and a clause here. Okay, and this is meaningful for different applications because you have simplified the text into these smaller units, and you can do inference and reasoning on these smaller pieces instead of dealing with the text as a whole, unstructured piece of text. So you can again see that this could be modeled as a binary, as a chunking problem, right? Instead of named entity chunks, you have clausal chunks. You have a begin, start of a clause and an end of a clause. And again, you can model this as a sequence tagging problem. Okay? You follow that? Is that fairly clear? So at the beginning of a clause, I put a marker, and all the words within a clause are inside the clause. So each of them has a tag which says it's inside the clause. and at the end of the clause I have another marker which says that you are exiting out of a clause. Okay? And now each word has a tag associated with it, and I can use my sequence tagging model that we talked about to tag new words, okay, new word sequences. And you have some numbers. So I won't delve into the numbers per se. If you want details, there are references in the slides. You can look at those references. I'm just giving you some sort of broad flavor on these tasks. Here's a sentence boundary problem we sort of saw in the beginning in the introduction. I want to annotate this sentence so that it breaks it at this point, right? So what am I going to do? I'm going to annotate each of these words saying that is it a sentence boundary or not, okay? So all of these words will get a no as a tag, and at this point I may say yes, okay? And then again go forward and say no, and for the word weak I say yes. Okay, so there's a tagging schema I can use to encode the boundary problem as a tagging problem, right? So in this case I would go about tagging each word with a no, and when I see DC it's still a no. So that would be the difference between these two examples. So this will have a yes here and this will have a no here. Now the classifier has to figure out how to optimize the error, minimize the error given features of the context, lexical features, the word-based features, the surrounding features, and so on. Okay, so and some of the features like morphology, we talked about these features. I won't repeat it. And training a maxent classifier, we get a very high accuracy. Okay, it's almost a solved problem, almost. However, when you that's on edited text, clean edited, newspaper-like text. But if you were to look at email data, which is something that we are interested in, people don't obey any of these things. So if you take that kind of trained model trained on this kind of clean text and apply it here, we get garbage. Okay, so there is issues here. How do you format this email so that we can do something useful out of it? And that's still a challenging problem to process this kind of unstructured email. Okay, and I'll give you a couple of minutes to just stare at it. You see all kinds of phenomena going on here. The ellipsis, this is called ellipsis, which is ... It doesn't mean there are 3 sentence boundaries there. It's just that people have, we all do that. So multiple exclamation mark. We also, as part of understanding emails, you want to recognize that this part of it is an address. Okay. Now again, you can encode this problem as a tagging problem, right? So this part of the text can be annotated with address tags, saying that this part of it, it's an address. But then you'll have to have annotated data. So one of the biggest issues I think Patrick might have mentioned is how to train the classifier once you have data is almost known. We have lots of tools to do that. But to build that kind of data that is meaningful to train classifiers requires human effort. It's as tedious as writing rules. Okay, there are ways of speeding up that kind of process of annotation, things like active learning and stuff like that. We may not cover that today, but ways of speeding up the annotation process itself, so that the learning programs can do a better job. Instead of annotating examples that the learning program knows how to solve very well, we try to give it examples that are on sort of the boundary, where the program doesn't know whether it should go this way or that way. Okay, so that kind of those kinds of examples are more useful than repeatedly solving the same problem over and annotating the same problem over and over. Okay. Here's a sentence boundary problem. So this is typically how a speech recognition output looks like. And this is how people talk. This is a pretty good transcription. But the thing to notice is that it's one long stream of words. There's no sentence segmentation, boundary, semicolon, nothing, comma, nothing of that kind of things that you see in edited text. And you have to start making sense of this, barrage of words. And things, what I talked about, false starts, things like this. I am, okay. Pauses, there are dead pauses, filled pauses like this. Edits, so things that the speaker is editing out, or discourse markers, which are good clues as to where to break them into clauses or some smaller units instead of taking this whole, I don't know, maybe 50-word sequence and trying to make sense of it. Okay, so again, these kinds of problems are other examples where you can encode them as a tagging problem. Okay, so the repetitive theme I'm trying to get to is that many problems, if you think a little hard enough, you can start modeling them as tagging problems. Okay, and there are some results. We have some good results and so on. So I won't delve on that. So here's a different way of thinking about tagging. So most of the tags that we saw so far are very basic tags in a sense, very simple tags. Okay, the tags don't have any meaningful structure in them. You said it's inside a named entity or outside a named entity or on the boundary of named entity, or you said it's a verb or a noun or a preposition or an adjective. They're sort of atomic symbols. They don't encode any richer structure inside them. But there's nothing stopping you saying that these tags have richer label, richer meaning, richer structure in them. So that's what we call super tags here. Some of the work that I have done here is to look at the problem of parsing. Parsing, as we saw, was to infer the relations between words, right? Words and their between two words and label the relation between the two words. So that kind of parsing problem can be seen, for most part of it, can be seen as a tagging problem, except the tag sets are much richer than what we saw before. Okay, instead of saying that the word is control is just simply a verb, I'm going to say that it is a verb with two arguments, meaning it's an object and subject packed into this tag. Okay, so there is a subject to the left of the verb control and an object to the right of the verb control. Okay, so I have packed more information into a tag. Did you get that? So not only do I say that the verb is the word is control, I mean the word control is a verb, but I'm saying that it's also a transitive verb, and in English it so happens that it could take a clause on the right as well. So I make up another tag for that context as well. Okay, and when you have a relative clause, I won't go into the details of the analysis, there is yet another tag. So for each context, I'm making up another tag. Okay, and you might wonder, does it go infinitely many tags then, for each context? There is theory saying that there is only so many tags that you need to get most of the coverage of English. Okay, so it so happens that we have extracted about 5,000 tags of this nature. Okay, the point to take home is that the words are not just indicated with just simple tags, but have more complicated structure in them. Now, once you complicate the structure, the obvious consequence is the vocabulary of tags grows. Okay, from whatever 13 tags of simple parts of speech, we have 5,000 tags now. Okay, so the vocabulary of tags grows. And the ambiguity, if I don't show you the sentence, the ambiguity for the word control is all these tags, and there are many more here. Okay, not just the simple part of speech, but also these different contexts. However, given the context of the sentence, only one of them or a few of them fit well. Okay? So given the context of the sentence, only this tag makes sense. These two tags don't make sense. Okay? So you can, if you model that and get the right sequence of tags given the context of the sentence, most of the parsing problem is already done for you. Okay? That the word, as soon as I tell you that this is the right tag for the word control, then you know that it needs an NP to the left and an NP to the right, noun phrase to the left and noun phrase to the right. And you can go looking for it and easily you can get hold of it. Okay? Most of the tagging problem, most of the parsing problem gets solved that way. But that's where the scaling that Patrick talked about comes in. Okay? What do we have? We have about 4,727 labels, and we have features which we take as lexical, just lexical and part of speech features from the left context and from the right context. Okay? And as I was saying earlier, there is no dependence on the preceding decision that you made. So very, very simple disambiguation model. I don't even know what you told me, what it decided in the preceding step. I'm going to just take the lexical context and the part of speech context. So if you just take those as features, you have about 2 million features, 1.8 million features. Now think of this, this is the size of the matrix, and we want to optimize on this space. Okay? So the scaling things that Patrick talked about start applying at this point. Okay? Any case, so here's the results for this. For an HMM generative model where these scores are trained generatively, you get about 18.2 error rate, meaning on a per word basis, you're making 18 point, out of 100 words, you're making 18.2 errors. Okay? With a max-end model, you can drop it to 11.5. And here's something that it looks like this. If you take that and send it to the super tagger, which is a tagger that annotates super tags, it looks like this. These are the tags, and there are 4,200 of them with some scores and can be interpreted as confidences. Okay. So I don't know, maybe Patrick covered this. Instead of training an n-way classification problem, we model this as a binary classification problem. Okay. So for each of these feature contexts, we ask, does Ti appear, T1 appear here, or T1 does not appear here? Okay. So that's all. Yes.
So you built 4,000 classifiers?
Yes. Yes.
Yeah, I didn't mention this is I mentioned the one versus other classifier in this announcement.
Okay. We end at 5, right?
Yes.
It's 4:30 now? Oh, okay. 4:20, okay. All right. So I don't have to go through the slides, right?
Yeah, you can save some time by going only out to 3 decimal points.
Sorry?
You can save some time by only going out to 3.
3 decimal points. Okay. So simple extension. So once you have the tags, now because the fact that the tags have structure in them, you can unpack them. They are like bundles. You can open them up, and they come up with constraints. Okay, they're saying that the word whatever control needs an NP to the left and NP to the right, and then you can start using those constraints to establish relations between words. Okay, and that's essentially a flattened representation of the dependency tree. Okay, so most of the parsing problem can be solved, can be viewed as a tagging problem with enriched tag set. Okay, that's the message to take home there. So now let's see a different problem, a problem which is called surface realization. So imagine you're a designer of a dialogue system, and the dialogue system is a human-machine dialogue system. The machine has to communicate its intent to you. So I just took the train this morning. Amtrak has a reservation system where it asks me questions. Where do you want to go to? Where do you want to leave from? What train do you want to take? And so on and so forth. Okay, is it an expressive, whatever, SLR train or non-SLR train, right? So these are intents that think of a form being filled out in the background, and the machine is trying to ask the user for pieces of information that it can use to fill the form. Okay, as part of that form filling dialogue, one of the steps it is to ask the question to you. How does it form the question? There is some intent it's trying to communicate. That intent has to be verbalized, has to be put into text, or eventually synthesized, right? And that last step is called surface realization, meaning taking the text that it's trying to communicate and putting it into the right sequence is called surface realization. It's one of the steps in language generation. Okay, so imagine, and I'm not showing you the full sequence here. Imagine there is some background, some planner which has produced this kind of structure. So it needs to communicate this in the right order. That's what it's going to surface realize it. It's going to put this dependency structure into a string sequence like that. Okay, you can think of this as a reverse case of a parsing problem, right? So we went from here to here, right? But in generation, you want to go the other way. Okay, now don't worry about how the structure is created. For now, let's assume it's given to you, right? So again, this problem can be modeled again as a tagging problem, except the tagging that we saw in super tagging case was being done on a string. Instead of doing it on a string, now you have to do it on a tree. Okay, so given the features of the tree, subtrees, you want to assign for each word the right tag. Okay, the consequence of that, of assigning, so without the context of the tree, you have ambiguity. You have 2 or 3 tags on each node, and if you do the decisions right and you get the right super tag for each word, then you can again unpack it and you get the linear order constraints. You know that the word poachers will be to the left of control and trade will be to the right of control. Do you follow that? So because we are dealing with these enriched tags, you can get the super tag done on the tree, and you can unpack the tree and get the sequence of orderings. Okay, so this is also called as a surface realizer. So each super tag tells you the place where it attaches to its mother, either to the left of it or to the right of it, and so you can infer the ordering and create possible sequences. In some cases it's ambiguous whether it goes in one place or the other, so you can create ambiguous strings of this sort and you can encode them as a finite state machine, okay, as a packed representation of alternatives. That's what a finite state machine is, right? And then you can ask, can I rank these sequences that are encoded in this finite state machine such that I get the best sequence according to my language model? And language model is something Jason might have covered yesterday.
Yeah, that's what we spent a lot of time.
Right. So
just to be clear, a language model is a model of a sequence of characters or a sequence of words. So the n-gram language models where we rolled dice to generate random text were one example.
Yeah. Okay, it's one way of scoring a string. Okay.
But here, this is being used for language modeling. This is a much more interesting model that takes syntax into account. You also built language models yesterday afternoon with probabilistic context-free grammars, which assign probabilities to strings, and in fact, you were evaluated on whether you assigned a high probability to strings you hadn't seen before.
So, yeah, furthermore, just because we are dealing with a tag set that has richer information in it, you can unpack it and exploit those constraints. If, suppose the mother doesn't have 3 slots, it can't have 3 children attached to it. These are constraints that are exploitable because these tags are richer in nature. Okay, so those are what I call as compatibility constraints. And if you do take into account those, in addition to the disambiguation decision rule, which is like a Maxent model, okay, which you might have seen this in Patrick's talk, this kind of equation, you get much further than treating them as atomic objects, because they are not just atomic objects, they are objects which have internal representations in them, right? So let me, furthermore, these things can be represented in an n-dimensional space. So each super tag can be broken down into n dimensions, and each of these n dimensions have some linguistic meaning to them, like whether it's an active voice. Think of these as 1, 2, 3, 4, 5, 6, 7 dimension space, and each of these are axes in that 7 dimensions, and a super tag becomes a point in that 7 dimension with these as the values of the axes. Okay, and then you can ask the question: can I get the super tag that is the closest to some legal super tag based on classification on each of these 7 dimensions? Okay, so those are some of the details, but you can look at that. I'll skip those slides, not relevant. So now let's go one step further. So now we talked about words and tags, and we go to a problem where the length of the tag sequence need not be the same as the length of the input word sequence, which is a translation problem. Okay. Feel free to stop me. Okay. We have about half an hour to go, so don't sleep. So here's an example. So I need to make a collect call, and anybody speak Japanese here? And that's the Japanese, hopefully the right Japanese transcription here. Okay, and typically what is done is alignment. Alignment means you are assigning the Japanese word to the corresponding English word. Okay, so I guess this is watashi wa. Am I right?
I just know that one.
I know that word too. I know that word too. Anyways, so what you're trying to do is basically draw lines between words and its image on the other language. Okay, so that's the alignment problem. Now, the beauty of everything that we talked about so far, once I give you this alignment, I can view that as tags for each word, except now the tag vocabulary is the words of the other language. Do you see that? I can represent this as I/watashi wa, or need to this complicated verb here, right? Except that the problem scales. It's much larger tag set, not just 4,000 or 13, but more on the order of hundreds of thousands of words. Okay, now. So and so also here, this simply shows the alignment between, and I've indicated that with lines here. So what we've done with Patrick's tools is to view this as a sequence tagging problem. Okay, we have scaled our tools to look at each word and its lexical context, meaning just like we did for super tags and part of speech tags, except the tag vocabulary is now the Japanese vocabulary. Okay, and okay, so that's what we call as the sequence lexical choice problem, meaning given the sequence of lexical items and that you infer from the alignment, okay, we run the alignment to get these lines that I showed, and you'll probably see more details on how that alignment is done later on in this course on machine translation. But I won't cover that. But once you have the alignment, you can view it as a sequence of lexical decisions that you're making. Okay, and for languages that are may be closely related, that's a reasonable model because the words don't move around very far from their source word. Okay? But for languages like English Japanese or English Hindi, where the verb comes to the end of the sentence in Japanese or Hindi, and in English it comes roughly in the middle of the sentence, the distortion, meaning the place where it ends up and the other side, is very large. Okay? So what we've been looking at is something called the bag of words lexical choice model, which we also call it the global lexical choice model. So the idea here, okay, I can skip that. Okay, just a brief thing about, so this equation is again familiar from the named entity stuff that we looked at. So we're trying to decide in this case, the English word, given that the source language was French, okay, and we are looking at the ith position of it. So that's the sequence lexical choice model. Okay, at each point I in the source sequence, you're trying to predict what should be the best EI. Okay, very similar to other tagging problems and so on. And this can be encoded as FSTs, and all that details are in the papers in the slide. But I want to just go to the other way of thinking about it. So let's say you don't want to do an alignment or establish a relation between the word and its image on the other side, because sometimes it's hard. Sometimes multiple tokens map to multiple tokens on the other side, and it may not be one-to-one mapping. Okay. So for all those reasons, what we are trying to do is to estimate the probability of finding a word in the target sentence given entire source sentence. All we are saying is, don't worry about the order of the words in the target side. Just tell me what words should I produce independent of the order. So take the source sentence, I would like to make a collect call, and give me the bag of Japanese words I should produce. Okay, let's break down the problem of translation as 2 steps. Let's select the words and then put the words in the right order. Okay, so selecting the words now becomes more like a call type classification style problem, where given this text, source language text, I need to give you multiple tokens from the target language vocabulary that make sense for this source word. I am not worried about the order of the words yet. Okay. So the training examples look like this. The positive examples when the word appears in the target, and it's negative if it doesn't. So if the watashiwa didn't appear as a word in the target side, then all those sentences become negative examples for the word watashiwa. Right? Now, in the call type classification or the Reuters classification, the newswire classification, typically the number of classes are in the order of tens, maybe hundreds. Now we are dealing with, if you model it this way, we are dealing with the number of vocabulary items on the target side. Furthermore, if you want to model repetitions, you have to model that repetitions, like the word I probably happens multiple times in a sentence. If you want to be faithful to that, then you have to index those somehow. So the number of classes again grows. Once again, we resort to the binary classification way of dealing with things. Is the word there or not there kind of classifiers. Okay. So what's the decision process? So once you run the classifier, then you get all the words that are above some predefined threshold. Score wise, if the classifier says, oh, here's watashiwa with 0.99, here's another word with 0.98, and so on and so forth, you chop it at some threshold, and that's your bag of Japanese words that you want to translate with. Okay. Okay, schematic about it. Here's the source sentence. You get this source bag of features, and these could be like n-gram features, contiguous features from the source side, and then you produce a target bag, and then do the reordering. Okay, so the point is that both these steps have scaling challenges, meaning it has to scale. Suppose I produce a bag of 20 words here. How am I going to reorder them? How am I going to put them in the right order? Okay, and one way, let me recap here. In the local sequence model, where you have the word and its associated image from the target side, it looks like this. So for each target word, for each position I, you have a classifier. So instead of 4,000 whatever, Japanese vocabulary number of classifiers, for each position you have a very small set of classifiers. Okay, whereas in the bag of words model, you have as many classifiers as there are words in Japanese in the corpus that you have. The input features are pretty similar. In one case, you take the local context into account, I minus d and I plus d, and you compute some lexical features in that context. In the other case, you take the full sentence into account from 0 to n and compute the bag of words. The word probability is pretty much the same. The number of classes, there is one per target word or phrase. And the training examples here, there is one per sentence pair, meaning there is a positive or a negative for that particular word or classifier. In the other case, the one per source token. For every position in the source sentence, you have a classifier. Some of the distinctions. Okay, so once you have a bag of words, you have to do some permutation. This is not related to learning, but it's another part where scaling is an important issue here. So given 20 words in the bag, what do you do with it? Given 3 words, I can build a permutation of the 3 words. I have 6 different ways of permuting them. Then I rank it using some of the techniques that we talked about, the language model way of ranking. Okay? But if there are 20 words, then I can't really compute 20 factorial. Okay? Maybe I can, but in a smarter way, but there are memory limitations, and so one of the tricks that we do is to limit the size of the window and how much movement these words can have and so on. But this is work in progress. If you want really the details, you can look at that paper. We get very good results and so on using these techniques, not focusing much on the results here. So there are 2 challenges though. One is repetitions. How do you account for the number of times? And I kind of alluded to, maybe indexing each word with the number of times it appeared. That's kind of a hacky way of doing it. We don't have a good solution for that. The word like the or I is going to appear many times in a sentence. So maybe chopping up this source sentence into clauses like the way we talked about, so that you don't have this repetition problem happening, may be a good idea. We don't know about that. Synonyms is a very classic problem that happens here, that because words get translated in many ways by many people, they may use different so-called synonyms to convey the same thing. So those things surface become apparent here. The same word can have multiple ways of mapping into the target side, and all of them become part of your bag. How do you know if word A and word B are synonyms of each other? That's not clear. So these are some of the limitations of this approach. So there are extensions of that if you want to look at that paper and so on. So, let me switch gears and the next maybe 15 minutes cover a couple of other ideas. So we've been talking about tagging, we've talked about sequence tagging, and we've talked about how enriching the tags with additional information, syntactic information, has benefits for parsing, for generation, and we looked at translation as a large tagging problem, very large tagging problem. I'm going to talk about a little bit on how to go about using human-human dialogue data and inferring structure from it so that you can possibly build a human-machine dialogue from that sort of setting. So the typical way of human-human dialogue, human-machine dialogue creation is that somebody sits down and thinks about what this dialogue should be and crafts a call flow. If you're in the state, the system and has this kind of input and is looking for this kind of additional piece of information, then it should say why, and so on and so forth. So people think of it like a flow chart. Okay? People design these flow charts from experience of the domain or from data they have sampled by looking at human-human dialogues. So the biggest problem with that is that it's, of course, intensive, time intensive, and error prone, because the human cannot visualize every possible situation that the dialogue system gets into and have a if statement or a case statement there. So the question is, can we combine data that you have collected from call centers, human-human data, with some pre-crafted human-machine call flow structure and come up with some hybrid approach? Okay, so that's kind of the goal of this research. So the idea is to, can you predict or infer models that predict the structure of task-oriented dialogues? And we happen to have, catalog ordering dialogues where people are calling in. Think of the JCPenney or Sears catalog ordering that you might have done, not on the web, but on the telephone, or you used to do that, where you order items from catalogs by talking to a real human being on the other end and stepping through the dialogue sequence. What order you want to order, what item you want to order, where does it have to be shipped to, how are you going to pay for it, etc., etc. So there is a sequence of tasks or subtasks you need to accomplish to get to that end of the dialogue. So this is the current paradigm. I talked a little bit of that. So eventually what we want to do is to, given a human-human dialogue, you want to infer this kind of structure on it. You want to infer that there are utterances and clauses. We want to annotate each of these clauses with dialogue acts, which means the speech act. Is it a question? Is it an answer? Is it a request? Okay, that kind of tagging. Again, it's a different vocabulary of tags, but can be modeled with the same kind of things that we talked about before. Then there would be a notion of a chunking, just like you have a chunking of groups of words. There are groups of utterances can be put into a so-called as topic or subtopic. Are you talking about payment? Are you talking about shipping? Are you talking about ordering? Okay, so the entire dialogue, there may be chunks of it which are related to a particular topic, subtopic. So that's the kind of thing. And then there is a task level one. It could be an ordering task, it could be a cancellation task, and so on and so forth. Okay, problem reporting task, and so on. So eventually, given a dialogue, a human-human dialogue, we would like to infer the structure. Part of the reason to infer this kind of structure is to do human-machine dialogue modeling. What can I predict what subtask is going to come next, given that I have seen this subtask? That's kind of the modeling problem. Can I predict what should the system say, which is the utterance, given this entire left context of the dialogue? Okay, things that those are modeling issues. You could also do, for people in call centers are interested in how well did the human-human, dialogue go, in terms of efficiency and so on. So you may want to do search and retrieval on these kinds of structures. How often did the human agent, suggest an alternative, product when a person has bought some, maybe shoes? Did she suggest an appropriate additional product and things like that? So those are questions you can ask once you have represented the dialogue in this structure. So here's a sample dialogue, and the agent and the customer are alternating here. And you want to structure that into something like this. So there's an order item task, there is an opening sequence which says thank you for calling XYZ catalog, and then there is a, so this utterance is tagged with the word hello, or this level of tagging is called dialogue act tagging. Okay, there's a request for an order, there is an acknowledgement, okay, on both parties, and this whole sequence of exchange of conversation is called an opening subtask. Okay, and then there is a new subtask which is she wants to know the contact info. Can I have your home number, blah blah, and so on and so forth. And then there's another subtask which is shipping address, and so on. So we saw a little bit of this. So what we are doing in this case is, these are ongoing projects, by the way, is to first segment them. We saw a little bit of this and before, how to break it down into clauses by removing all these kinds of speech-related phenomena, and come up with some sequence of cleaner set of clauses. Dialogue act annotation, there is instead of 13 tags, we happen to have 67 tags, which have meaning in this domain, which makes sense in this domain. Partly because we need to generate, so the system needs to say need to verbalize how to say request in account information or something like that. So these are some of the tags that you see, and there can be, there is a type and a subtype, so it could be explain catalog, explain order info, and so on and so forth. So these are meaningful for generation purposes. And again, we use the same Maxent Llama model to do the prediction. So we want the best dialogue act given some feature history. And these feature histories, as we're talking about, there's a lot of dialogue context that you want to use in that feature history. And we predict the best dialogue act for that given utterance. And there are numbers there. So the next step is to predict the hierarchical structure, which is how do you get opening to contact info to order item, and so on. So again, this is modeled just like we modeled the chunking, okay, begin, inside, and out. So here also you can say, so it's the subtask began at utterance I, and the rest of it is in the middle of the subtask ST, and then UJ is at the end of subtask. Okay, and now you have turned it into a tagging problem, same story again, and you get the best sequence of subtask labels from this. So this is called the chunk-based model. So the theme is that eventually, okay, so one small twist is that the chunk-based model doesn't give you the full structure that we were talking about. It just gives you the sequence of chunks. Okay, so you can go one step further and infer the dominance relation. How is these subtasks related to each other? And you can use a parser to do that. I'm not talking about that right now. Okay, I think I may not have time to cover this topic, but this has other interesting ways of combining acoustic information and lexical syntactic information in a tagging-like setting to do prosody. Prosody is, how words are spoken, and there's meaning in yes versus yes. Okay, even though lexically it's the same, the prosodic contour, the acoustic information has a bearing on how the word, how the utterance is interpreted. And there's much to be said there. There's a reference there. But eventually, what I hope I have conveyed is that many of the decision problems, well, let me back up. NLP has a lot of ambiguity. In each of the steps, there is ambiguity. We have to, the idea of converting an unstructured text on unstructured speech into something meaningful requires you to have a handle on that ambiguity. Okay? And to resolve that ambiguity, we use things like machine learning tools and appropriate linguistically motivated features to resolve that ambiguity or get a sense of how to go about resolving that ambiguity. One note I want to leave you with is, let's see if I can flip through this quickly, let's see, we looked at that pipeline, and because the ambiguity cannot necessarily be resolved in one best output, so you have to have a way of encoding multiple outputs that the classifier may say, because you don't know whether the first best is the right one or not. It might be wrong down the pipe. So their ongoing work is to see how we can extend this sort of pipeline architecture so that you can broaden the pipe and produce multiple solutions and pass it down the chain. Okay? Because the ambiguity may not be resolved in one step. And there may be other kinds of discourse information or contextual information that might resolve that ambiguity down the chain. So instead of getting the wrong solution and getting a greedy solution up front, you want to propagate some weighted set of solutions down the pipe. And there is much work to be done in that space in case you are looking for PhD topics. All right, I'll stop there. So there are 5 more minutes if you want to ask questions or comments or feel bored, talk about something else as well. The presidential
I wanted to
campaign.
make a quick comment.
Yes.
So Srinivas has been talking about Llama much more than I did. The difference between Llama and the other software I described is basically we did, and Srinivas helped me a lot of tricks to allow Llama to scale to an enormous number of classes, I think up to hundreds of thousands, something you can never do with the off-the-shelf software. But this is, you won't run into this data in an academic environment, so don't worry.
So was this useful? Did you get anything out of it? Yes? Do you think you'll go on to do grad studies in NLP now? Or are you going to run away from it?
I learned some cool acronyms.
You learned some acronyms. Well, that's always good. Yeah, thank you.